Chapter 1 is about displays of data. Graphical displays can convey sophisticated or subtle messages that simple numbers can't. The right graph or plot can reveal surprising results that may inspire a different line of questioning, or it may reveal previously unknown truths. For example, in an famous early example of epidemiology, the 19th century physician John Snow plotted the addresses of cholera victims on a map of central London. This revealed the location of a water pump that was the source of the epidemic. Chapter 1 Objectives. First, we need to define individuals and variables, get some common language, describe variables as categorical or quantitative, describe the distribution of a variable, construct and interpret pie charts and bar graphs, construct and interpret histograms and stem plots, and construct and interpret time plots. To begin with, statistics is the science of data. The first step in dealing with data is to organize your thinking about it. So, an individual. These are the objects described by a set of data. So individuals may be people, but they may also be animals or things. A variable is a characteristic of an individual. And this is what we're trying to get information about. There are two types of variables we're going to consider. Categorical variable, and that places individuals into one of several groups or categories. A quantitative variable takes numerical values for which arithmetic operations like averages make sense. So, examples of categorical variables. Gender. We usually categorize people as either male or female. Those aren't numbers, they're just simply classifications. Marital status, married, single, divorced, etc. Suppose college majors, art, business, course mathematics, and so on. Car colors. These are all different ideas of categorical variables. Quantitative variables, on the other hand, take on numerical values. The ages of people, for example. The heights of people. Number of children per family. Temperatures, and salaries. So in these cases, in all of these cases, actually the average of these variables makes sense. So suppose we have some data that were collected on students in a class. The individuals are the individual students, here sort of identified with the letters A through F. We have a total of 8 variables. These are characteristics of the students. So the student's age, gender, height, GPA, and so on down the list. The categorical variables, these are gender, class standing, birth month, and favorite color. These can be classified into categories, but there is no meaningful numerical average or anything like that. The quantitative variables, in this case, age, height, current GPA, and shoe size. Now, an exploratory data analysis is the process of using statistical tools and ideas to examine data in order to describe their main features. So we begin by examining each variable by itself. Then we might move on to study the relationships among the variables. So in the case of the data I just showed you for a particular class, we might look at the distribution of the ages, the gender, GPAs, and so on. Then we might actually be interested in looking to see if there's a relationship between, say, age and height, or age and GPA, or something like that. We always begin with graph or graphs. And then we can add numerical summaries of specific aspects of the data. To examine a single variable, we want to graphically display its distribution. The distribution of a variable tells us what values it takes on and how often it takes these values. Distributions can be displayed using a variety of graphical tools. The proper choice of graph depends on the nature of the variable. Categorical variables, for example, are often represented by pie charts and bar graphs, whereas quantitative variables are often represented using histograms and stem plots. So, the distribution of a categorical variable lists the categories and then gives the count or percent of individuals who fall into each category. Pie charts show the distribution of a categorical variable as a pie whose slices are sized by the counts or percents for the particular categories. Bar graphs represent each category as a bar whose heights show the category counts or percents. So the taller the bar, the more counts or the higher the percentage that particular category comprises. With pie charts, the larger the piece of pie, the larger the percentage of the whole it represents. So here's an example. Suppose we're measuring solid waste, and the variable is the material. So it takes on many different values. We could say we're looking at food scraps, glass, metals, so on and so forth. Now, representing this as a pie chart, we have each category listed, and it's the size of the piece of pie is proportional to the percentage of the total it represents. The bar graph in this case shows the proportion or the counts as the height of the bars. Now in the case of a pie chart, notice for example paper is obviously the largest percentage of solid waste. In the pie chart, the size of the pie, the piece of pie associated with the paper, shows how much that is paper takes up relative to the entire amount of solid waste. Whereas in the bar graph, we clearly see that paper is the biggest, but we also can easily compare that to any of the other categories. So it's easier to compare different categories in a bar graph. Now for quantitative data, the distribution of a quantitative variable also tells us what values the variable takes on and how often it takes those values. There are some slight differences that I'll describe in a minute. Histograms show the distribution of a qualitative variable by using bars whose height represents the number of individuals who take on a value within a particular class. Stem plots separate each observation into what's called a stem and a leaf that are then plotted to display the distribution. In this case, the advantage is a stem plot actually retains the original value of the variable, whereas a histogram doesn't. So, to construct a histogram, we divide the possible values into classes of equal width. Then we count the number of observations that fall into each interval, and draw a picture representing the distribution. Bar heights are equivalent to the number or percent of observations in each interval. So, for example, suppose I have weight data on students from an introductory statistics class. Well, I choose to break up the classes into intervals of 20. I could choose another interval, it doesn't matter. The important thing is that the intervals are all the same width. So here we have the classes from 100 to just under 120 pounds, 120 to just under 140, 140 to just under 160, and so on. And then we simply count the number of values in the data set that belong in a particular class. So we have the frequency or the count in the column on the right. We can then construct a histogram. Notice the height of the bar is equal in this case to how many values fit into that category. Now, stem and leaf plots. This is also for quantitative variable. We separate each observation into a stem that represents the first part of the number and a leaf, which is the rest of the number. Write the stems in a vertical column, draw a vertical line to the right of the stems, and write each leaf in the row to the right of its stem. And we can put these in order if we want, but that's not necessary. So let's take the weight data again. Here I'm choosing to construct stems that are made up of the first 2 digits. So effectively these are classes of width 10. So, and the leaves are just simply the ones digits. So we put these in order, 10, 11, 12, 13, on down the list. Note 10 here represents those weights that are in the hundreds. The 11 represents 110s, the 12 represents 120, and so on. So we start with each number. In this case, 192. The 2 then is the units that goes into the row with 19. For 152, the 2 goes into the row with 15. 135, the 5 goes in the row with 13. And we just fill in the rest of the numbers by going through the whole list. So notice in this case, for example, 20 and then the line 3 actually means 203 pounds. So we retain that number. The stems are in terms of tens. The leaves are ones. Now, if we kind of look at this and turn it 90 degrees, the stem plot actually looks basically like a histogram. And that's not by accident. That's the purpose. Now, if there are very few stems, that is, when the data cover only a very small range of values, we might want to create more stems by splitting the originals. So if we have weight data, for example, from 150 up to 179, there are really only 3 categories if we use the previous scheme. We have 15, 16, and 17. So we might want to split the stems and create, in this case, 6 different categories, or 6 different stems. Now the leaves 0 through 4 go in the first 15 stem, and the leaves 5 through 9 go on the second one. So for example, the data point 150, the 0 goes on the first 15, like so. And for 156, because 6 is between 5 and 9, the 6 goes on the second 15. And then we can fill out the rest of the numbers. And if you take a look at that, it should make sense. The second split stem represents the numbers 5 through 9. The first stem represents the leaves 0 through 4. Now, describing distributions. In any graph of data, we're looking for the overall pattern and for any striking deviations from the pattern. We can often describe the overall pattern by its shape, center, and spread. An important kind of deviation is called an outlier, and that's an individual that falls outside the overall pattern. So in this case, the class on the far right there is an outlier, appears to be an outlier because it's far different from the rest of the pattern. So here's an example. In this histogram, we're showing the distribution of percentage of foreign-born residents and the number of states. So this is the 50 states. And For example, this bar and the second bar has a height of 13 because 13 states have between 5.1% and 10% foreign-born residents. And you can kind of tell that the majority of the states, 20, have between 0 and 5% foreign-born residents. So to describe the pattern, the shape we begin with. So notice we have a peak at the left, and the overall shape is skewed. It's heavy on one side and lighter on the other. The center, well, we might describe the middle number as around 6% or something like that. We might talk about the center as being the average as well. The spread, the numbers range roughly from 0 to 30%. It's kind of hard to get specific values from a histogram just by looking at it. It may not be that accurate. Outliers, there's nothing obviously different from the overall pattern here, so the outliers. Now, with histograms different from bar graphs, different class widths allow different levels of detail and may suggest patterns. So we'll take the histogram of the percent of foreign-born residents again. Here the classes were 5 percentage points wide. So if we want, we can construct classes that are only 2.5 percentage points wide, and then count the number of states that fit into each of those classes. So we're just making it a little bit finer. Notice this does give a lot more detail than the graph on the left. Notice also too, I want to point out, even though there's a gap here, this observation really doesn't deviate from the overall pattern. There's just a hole where there are no observations. So we wouldn't call that an outlier. Now here's a case where we have two peaks on a histogram. And oftentimes this will suggest that there are two types of data included here. For example, we're measuring the number of states. Well, there are two peaks here, so this sort of suggests that there are two different types of states represented, which in this case does make a bunch of sense, because we're talking about the percentage of high school graduates who took the SAT. Well, there's another popular test called the ACT, and it could be that the states with the two peaks here, the difference between them has something to do with that other test. Now, when describing distributions, we often say that a distribution is symmetric if the right and left sides of the graph are approximately mirror images of each other. A distribution is skewed to the right if the right side of the graph is much longer than the left side. It is skewed to the left if the left side of the graph is much longer than the right side. So a symmetric distribution, we can draw a line down the middle and we've got mirror images on either side. Skewed left, notice that the values trail off toward the left. It's top heavy on the right, so we call that skewed left. Skewed right, the values trail off toward the right. Now, a time plot shows behavior over time. Time is always on the horizontal axis, and the variable being measured is on the vertical axis. For a time plot, we look for the overall pattern or trend and any deviations from the trend. Sometimes connecting the data points by lines can emphasize the trend. We also look for patterns that repeat at known regular intervals, like seasonal variations or things like that. So, for example, here we have a time plot of the percentage of a particular class that are made up of freshmen, and from the years 1985 to 1993. It kind of bounces all over the place, but there seems to be a fairly clear upward trend. That is, beginning in 1985, there were around 11% of the class were freshmen, and by the end of it, it's above 50%. So there's an upward trend. Here's another example of average tuition and fees broken up by public and private schools. So clearly, in both cases, the tuition and fees are increasing over the time span from 1970 to the year 2000, but it's fairly obvious that the private schools are increasing at a higher rate. So, to review, we defined individuals and variables. We categorize variables as categorical or quantitative. Describe the distribution of a variable. Construct and interpret pie charts and bar graphs. Construct and interpret histograms and stem plots. And finally, construct and interpret time plots.